But that's actually the peer observer thing is actually tangential to any stuff that we normally have for tenure, like track and promotion, so that they can't hold it against you, you know.
Right.
But I don't know. I think it's actually not a bad idea. Like maybe, you know, your class would be occasionally audited by someone in the department, or they do audit us during cycle years. So I think spring 2025 is going to be the time to do a full cycle audit. So and they can just choose randomly to come to class.
Nice.
Walk into a classroom and they're there, they sit and take notes. And so I've never been audited, period, in 7 years. I've never had another instructor come to my classroom. So I don't care. I actually think it would be interesting.
Now, do you think it would be just any random professor or somebody in SSE that would maybe have an idea as to what you're...
Well, you know, I would actually prefer somebody that knew what I was doing, but they're pairing
maybe
us.
Better with somebody who does.
I think it's interesting to maybe have somebody from like school education come and talk about like maybe, you know, limitations to the pedagogy of, you know, the lecture structure that we've sort of taken on as the core of the SSE type classes. Like maybe we have a different approach to the way we teach courses than they're teaching it elsewhere, and maybe they've learned some stuff or are more effective.
Right.
I think other disciplines tend to be a little bit more malleable when it comes to that. I think that they have a little bit more reactance to like new ideas and new processes. One of the things that we've been discussing, a few of us in the department, is the idea of like what's called positive grading or grading for growth. And growth grading is like a situation where you don't look at it from the perspective of going, I started with 100% and I just go down from there. You know,
right.
You start off like where you have a net differential, right? You can perform poorly on something and then perform well on something else, and essentially those things can balance out and tally out. And so I've been trying to look for opportunities to integrate those things within the coursework. So.
Well, that's a perfect segue, because I've been wondering what exams are going to look like in this class.
Well, I will give you examples.
Okay.
I will provide you.
So it's going to be a workout, like a sheet, and we have to work it out, and...
It kind of depends, actually.
Okay.
So I've done both for midterms. I have done multiple choice, and I've done short answer questions.
Okay.
I don't really have a lot of math in this.
Right.
No.
And that's where I'm trying to like figure out what it would be like. Is it
we're gonna talk briefly today about one of the things that you talked about. I want to discuss kind of the idea that you discussed, which is the idea of how to implement this at the level of a algorithmic process.
Okay.
So, one of the things that I will say in sort of the definitive level right now is you don't actually, like in truth, you don't actually do this by hand. There is no do this by hand anymore, because
I wouldn't see how you would be.
you can do it for small data sets.
Well, yeah,
I
very.
can have you do this, you know, for 20 or 30 data points.
Even
But
that would.
it's not as hard as it seems, right? So let's look and see. Right, we talked previously. What do I need to do? I need to develop the mean, and then I just need to iterate through with means of X and means of Y. So
Right.
the first operations we're going to work with right there are these two operations, right? So actually, even though these are at the bottom, these are the first two things you do. That's actually time intensive from the perspective that we're looking at, right? So the scale of n determines how many ops it takes to aggregate it, right? So you're going to have an aggregator operation, and then you're going to have scale of n. So you're going to create a variable that is assigned to the mean of y, create a variable that's assigned to the mean of x. You're going to take essentially the means of the columns, summation over numeration, And then you're going to go up and do this. Now how do we implement this at the code level? What is this? What is a sigma? It's a loop.
Summation?
Right.
Right? It's just, a summation is just a loop. It's a for loop.
Yeah.
For n,
Right.
add
For loop.
value I to aggregator for element, add loop for I for element, right? So down here, once again, these are loops. So you can iterate to two variables within the same loop. You could say, let me iterate through for all values n, do mean y and mean x simultaneously in the same loop, right? So just keep iterating through element to element. And then you have to establish, since the mean of x and the mean of y have to be established before that calculation can even be started with, right? So we have to calculate characteristics of the data set before we actually start with any process of regression. So that's problematic because we have a little bit of overhead before we can even start doing anything. If you have a high P, high dimensionality, this changes, right? So let's talk about that. Let's go forward here a little bit. Let's get past quite a bit. All right, so we were discussing Wednesday the idea of a multivariate regression. What does a multivariate regression look like? I asked you guys to kind of think about it. Anybody have any thoughts on the concept? I said occasionally the idea of holding one element fixed while adjusting the others is problematic. Anybody think about that afterwards? Or do you just immediately forget me when I'm not in the visual space? It's all right, I understand that. It's not very memorable. So let me say this one. I can do one at a time, right? So I can tell what x1 is to y, and I can tell what x2 is to y, right? And my podcasts and my YouTube videos. And if I put more advertisement out, I tend to notice a correlation with an increase in advertising. So I would say, yeah, each one has its own linear functionality. But what if I want to put it all together as a system? We know that in reality, things within the natural world operate as systems. So what if I don't change the number of ads on my YouTube advertisement, but I increase my podcast coverage? I can do that, right?
Yes.
They're relatively independent from the perspective of saying that they don't really change anything. But what did we talk about previously? The idea of saturation. If I put too many ads out on too many disparate platforms, I will end up with a diminishing return because people will get sick of seeing and hearing the same ad over and over again. So in reality, we may end up actually having a diminishing return by cranking up the values for each of these too much. So if I say my Y target, right, and I have, of course, my intercept characteristic plus my first coefficient relative to my first element, right, so this would be element 1. If I say I don't really care what's over here, right, I just want to create a correlation in this space. So I put a little, I'll go ahead and draw a few more out, right? So beta 2 x 2 plus beta 3 x of 3. And keep in mind, this is not the only way I can do this, okay? This is just the linear version of it. Utilizing only a singular coefficient at first order means that each one of these will be representative of a linear functionality. But I could, in fact, actually add on a parameter such that it would be beta 4 times x of 3 squared, for instance, right? This would be a non-linearity that I would assign additive to the original linearity. Now what happens here is, since these are both x of 3, that whenever I have the linear coefficient, it becomes additive to that same space, all right? I just want that to be, I want that to be understood. Because some people say, oh, well, it's one, it's one coefficient to one parameter of the feature vector, right? No, you can have multiple different coefficients assigned to the feature vector. But at the moment, we're in linear. So start off with the most primitive idea. So let's say that I want to do something here, right? So I want to imagine that I've got some little knobs, right? This is a little stereo adjustment kind of thing. I've got little knobs. I can crank the slope of the line up and down. Now when I grab to crank that, hopefully this one, it's got a little gauge on it, and it goes up or down based upon how much I'm cranking there. So I say, well, I want to know each one. So what happens? I lock this one, right? And I lock this one. Don't move them. I can crank this one and see how much Y moves. I end up with an independent decomposition relative to the incorporation of Y. Now what's the difference between this and just assuming each of the linearities are independent? Nothing. It's the same thing, right? So if I make a characteristic that the output Y is just summational relative to that system, that is whenever I attempt to hold the system static or holding all other predictors fixed while attempting to regress the model. But there is a potential problem with this, and we'll talk about it in a minute. We say here that a balanced design scenario is relative to some x of j. Now, what do I mean x of j? J goes from what to what? It goes from 1 to p, right? So if you have j features in the space, we could call them p, but we're going to utilize the term, we're going to use j right now because, as I said previously, you can have more coefficients than you have features. So we could say that there are beta sub j elements and x sub j elements. They're in agreement with one another, right? You could have beta sub j elements with x sub p items. That would be like three features, and let's say 6 coefficients could be utilizing combinations of the features in other types of regressions. What I want to do here is I want to say x has a correlation to y in a decomposable fashion, and with all the variables staying fixed, I can estimate the test error for the coefficient characteristics separately and attempt to optimize them for external testing performance, right? I'm not necessarily going to optimize them based upon one fixed training set for the whole thing. I might have different parameterizations that I'm looking for the outcomes of each one, because if I have a different correlate, I am essentially saying that as I turn this knob, that adjusts, right? There's some value there. As the wave goes past, the buoy rises, okay? We assume that there is a correlation between the causal event and the subsequent event, right? We say we assume causality, but we should make sure that our data supports claims of causality by having enough significance to our findings, enough difference between the null hypothesis case and our assumed H of A hypothesis, right? Our experimental hypothesis, our thesis idea, in order to justify the idea that the reason Y changed was because I changed B1. Now, let's look at one of these things. I don't know. This one says expected change. Okay, we have expected change. Good deal. Total amount of change in your pocket. Let's do this one. I have the total number of coins and the number of pennies, nickels, and dimes, right? So total coins is x of 1, and the x of 2 and onward, right? X of 2 would be the pennies, nickels, dimes characterized, right? Can I change the total value of the dollar amount that I have in my pocket by adjusting or can I keep the total dollar value in my pocket static while adjusting the number of any coins while holding the others fixed?
No.
No. There is a nominal dependency based upon an interaction in representation, meaning that pennies, nickels, and dimes are actually distinct representations of the same underlying concept. Let me go here and see if you guys get this one. I like this one because it makes sense, but I also like to say, let's think about something that does truly share these parameters in a more tangible way. Atmospheric pressure, right, humidity, and dew points with regard to weather. What do those all correlate to? What are they all representations of?
Relative humidity.
Relative humidity, the dissolved amount of water in atmospheric systems. You open up a weather prediction app, right? Those are 3 features that you can come across in the weather prediction baseline. Try to change one and hold the other 2 static.
No, it's not possible.
You can't do it, right? It's because they're interrelated to one another. So what happens over here? While I'm trying to hold this one static, while I grabbed onto it and I'm holding it, I'm cranking it, it's turning with me, right? There's a gear inside of here, right? There's a little gear work in here that as I change this one changes, right? And there could be a whole clockwork of gears inside of here, interrelating these things together, meshing those constructs together. Let's think of a population for a moment that consists of 3 unique species: rabbits, wolves, and owls.
Poor rabbit.
Yeah.
I don't know, the rabbits are the rabbits from Monty Python. Poor wolves. Anyway, rabbits are, hey, they got the short end of the stick. All right, so they're getting eaten from all directions.
They also reproduce a lot more.
They also reproduce.
Yeah,
And
that's
will
what I'm gonna say.
So selective pressure will actually increase their reproduction rate because it will create that niche characteristic of as the pop drops, the resources increasing, female fertility and, male aggressiveness and yada yada. Okay, so we have a variety of factors we know. What did we just do there? We created a complex system immediately in our head. You can't change the number of wolves without doing what? Changing the number of rabbits, because the wolves have to have something to eat. Matter of fact, wolf gets desperate enough, wolf's going to eat an owl on the ground if it lands in the wrong place, right? So there's even a dynamic there where you don't have 2 totally separated apex predators. An owl can get a little baby wolf too, all right? So don't even think about it that there isn't the possibility of those predators being sort of on the same level food chain. So when I say that I can't hold one thing fixed while attempting, or 2 or n things fixed while attempting to change one element, wait a second. What do we do now? We can't do that, can we? Doesn't seem like it. The previous assumption was that we had to hold the other things fixed in order to be able to make reasonable assumptions about the interactivity between the target and the output. So what do? Are we stuck?
Mm.
I want you guys to think about it for just a couple minutes. Seriously, I want to just field some ideas. What do I do now? I've got my wolves, my owls, and my rabbits, okay? Owls go down, rabbits go up, wolves go up, wolves eat too many rabbits, rabbit population dips, wolf population dips, rabbit population goes back up, owls take over where wolves were, right? Over time, you have a bunch of little graphs all doing this together. How do I disentangle that in a way in which I can understand the characteristics underlying the total population of the dynamics of this system? Yeah.
So what we can do is if we consider, we can derive 2 equations,
Okay.
and try to change that one and change this one and minus that one.
Okay. So that a negative coefficient will fix the problem of subtraction.
Yeah.
Right? So if I have a negative slope, that fixes the problem of turning an additive relationship and a linearity into a subtractive relationship, right? So just think about it in terms of set theory. If I say this element, this element, this element, if I make this coefficient a negative value, then I'm technically subtracting the product of
Yeah,
the
yeah,
coefficient
okay.
times the elements of the set.
That's what I said. Like if
Okay.
you if we change beta one,
Yeah.
then if we need the beta one, right?
Yeah.
X1, sorry. X1 is our value we need to understand.
We
And
want to
X,
correlate x1 and y, right?
yes.
Yeah.
But X2 and X3 need to be constant. So if we change the X1,
Mm-hmm.
then X2 and X3 is going to change.
They could, yeah.
Yeah. So then we again take this is equation 1, and we take again equation 2 and we change the x2 and minus it to to remove those elements so that we can understand the x1 and y1 relation.
What you're describing is something called a data-driven approach.
That's like
Yes.
going back to when I heard you say decomposition, you create a y1 with beta naught plus beta 1 x1, a y2 with beta naught, beta 2 plus beta 2 x2, and so forth.
Correct.
And then you see how they look together, and you can change one and still plot all three on the same plot, but only one of them's changing.
1 second. Open my supplemental slides real quick.
Same thing, basically.
Okay. Any other ideas? Everybody in agreement with what they're talking about so far? Are you liking where they're headed? Why does it do the other one? It should duplicate. Never mind. Duplicate the other
It's the
display.
same problem.
Duplicates the wrong one. Let's look at something for a second here related to the regression of points on the system. As you say, I don't know exactly how these items change relative to one another, but what I had previously is that the null characteristic hypothesis says that the line for y plus y equals some beta naught, right, plus beta 1 x1 is independent from, or seems independent from, beta naught plus beta 2 x2, in the effect that whenever I change the value of x1 relative to y, and when I change the value of x2 relative to y, those changes are their own equations. That's how I was doing it previously with regard to each of the individual linear equations. But I said this has limitations in the effect that it doesn't concern itself with, and can't concern itself with because it doesn't have access to the information from the other sources. So I say, well, I can't really do this, truly, because what do I have? I have an array. So let's think about what we have for the array. We have values, we have an element number. So let's say we have n values corresponding to, it's one of those things where I like to say, well, if we start looking at our data set, maybe we can think a little bit about what we're actually seeing. So what do I have here? I have x sub 1, x sub 2, x sub 3, and what's the last element I have in the array?
X to the power x
I like putting it
xn
together this direction because it's totally confusing. It's a trick question.
xn.
No.
Oh.
This is this system. I just have 3 x's. What else is left in that?
Beta.
No. This is a data set. This is data. What is it? Y.
Oh.
I told you it's a trick question. Why is Y? Why ask Y, right? Okay? So I have some value, right? 3, 1, 2, 4, right? I have 3, 2, 1, and let's say 6. Notice something. I actually have what happened to each of these other values as a result of some subsequent change, right? So let's say that I did change 4, and I had, so this becomes a 3, and this becomes -1, right? And then this one is an 8 or something different, okay? I have no idea whether these numbers are gonna work together to be able to be independent, but what I'm saying here is, if you look at it from this data-driven perspective, right, this becomes elements of 1, 2, 3 samples, right? So each of the samples is a state of the process. If we think about the state as like taking a snapshot of a space, it tells us the composition and it tells us the relative characteristics. But what doesn't it do? It doesn't tell us how the components interact with one another. We can't tell that from a single sample. But as we get multiple samples together, now we have something that starts to give us some provisional interest or some provisional inference here. Let's imagine that for this particular regression, right, we have some space, and we've put our regression line through here, okay? And I'm going to say that as I change the slope, let's say we started off with this slope, right? So this is time t0, and this is time t1, right? I say it is an epoch, it is some time later on. I don't know how many steps I took in between, but I start off with an initial assumption. So let's think about what this looks like in characterization. So this is x, this is y. This is the feature space, right? So x of 1, the first of the dimensions that are provided in the feature space. Is this too low for you? Okay. On another axis here, we've done this before, right? This is error, and this is time t0. This is our initial condition. Now, where do I get the first equation that you were talking about? You said I just assume some relationship initially. How do I develop that assumption? So in order to have a model, I have to have numbers to assign to the coefficients beta. Where do those values come from? I guess. No, that's literally the truth. When you have no better position to start from, you randomly generate something.
Yes.
Okay?
Okay.
So this is what we call a stochastic methodology. There are other ways of doing it. There are procedural offsets, right? I could take it relative to the deviation characteristic of the sample offset, or deviation of the target, right? Or I could do a simple linearized regression for the local version and then assume similar characteristics for the combined effort, right? So if I take the coefficient for the regression that I did with the component x of 1 independent from x of 2 or x of 3, then I could start off with that as my initial assumption. So I have some error here, right? Some positive value of error. What happens over time as we get down to some value t1, right? Some transitive state value. We should hopefully, by processes, be doing this, right? We should be reducing the total error by improving this. So as I improve the fit of the line as r squared to 1, right? We should be gradually going down the slope of the surface of relative error, right? So at time t1, I'm hopefully at the bottom of the hill. So this is a bit of what would be called, or what is sometimes called, like a hill climbing or hill descent, like gradient descent methodology.
Gradient descent.
Gradient descent, okay? Have you heard of that before?
Yes.
With ML, okay, so we start off with a one-dimensional gradient that we're descending. Now what does this gradient look like? So if I'm standing here on top of this little surface, this little hill on the top, how far can I actually see? About that far, okay? I know the general direction this is going in. The version of this that I said was you jump out of an airplane, right? You DB Cooper out of a plane, right? You land in the middle of a valley, right? Between two big mountains here, and you land, and you got a little radio rescue, right? You go, my radio is not gonna reach from here, but maybe if I get on top of this mountain, I'll get enough reach to be able to do so. This is one of those like jungle mountains, and there's just this cloud cover, you know? You can only see a slight amount uphill. Everything else is just white with fog, okay? How do you get to the top of the mountain?
By
Just start climbing.
Start climbing. Which direction?
Pick one.
So you say start climbing.
The hardest direction.
The hardest direction. Right? You want the steepest slope. So you want to go up the element that has the direct, most direct, right? So this one's slightly less direct, seemingly, right? But we note here that maybe this one actually keeps going a little bit past the other one. So if my goal was to get to the absolute maximum position, I may never get there. But by utilizing this methodology, at least I'm not crippled with doubt and uncertainty at the bottom of the ravine because I don't know which angle to climb from. Okay? So when we say here we have a direction, we're going to have a couple of things. We're going to have a magnitude relative to the steepness of that slope, how inclined that slope is. That is not this slope. That is this slope. It is the slope of the error surface as a result of changes in beta, right? So this is created by delta beta 1. Change in beta 1 causes a subsequent position, and the subsequent position at some next step of the process, as a sequential process, takes me down to another location, right? So I get down to a second point. I then establish from there how much things have changed as a result, and then I assume what might be necessary as the next rational step to get down to the minimum error, right? You can think of these as these two things are the same, right? What's the error in this circumstance? Insufficient elevation, right?
Yeah.
So you increase elevation, you decrease the relative error in your height requirements in order to operate the radio. So we think about this as a metric concern. Hill climbing and hill descent are the same thing, except for in two different directions. Now, some of you may have seen this, and we'll only talk about it briefly, but I want to introduce it now because I'm going to talk about it again in neural networks. We're not really going to dive into it in a super big level because we can do this with a matrix transform compute, right? And use sort of a brute force perspective in order to try to converge on a reliable solution. With most of the data sets we have now and the amount of computing power we have now, these execute so quickly that it's not really a big deal, okay? But when we get to it later on, we start dealing with big data sets and high dimensionality spaces, we'll end up with another problem. So let's look here. We say this surface is shaped a bit like it's just a standard parabola, right? But we also have another space over here defined by beta 2, x sub 2, right?
Yeah.
That element will also have some surface. As well as beta 3, right? Beta 3, x3 will have some projection and some surface, right? Maybe this one goes out slow, dips quickly, and then comes back up. Now, what do I do here as I'm adjusting the knobs, right? So I grab the knobs and I start cranking the knobs. I'm going to end up being in different places. I'm going to move from position to position on the error surface. I'm going to jump down here, and then jump over there, jump down here, and jump over there, right? As I change the values, I see what degree of error we're encountering at that relative space in the surface. Now, what does this look like when I combine those elements together? Let's just think about two of these dimensions. Let's just say this one and this one, right? It curls in on that surface, right? Like a little sombrero. I don't remember if I have a version of this one here. I'm checking to see. I don't have it on this slide, so sorry. it curls in like a little sombrero, a little Mexican hat. Let me draw this a little bit better from a side perspective, right? So we think about it like a side, it dipped in with conic sections right inside of it. So I start my marble up here on the side, and I drop it. What happens to it? It's going down in based upon the direction of steepest descent based upon momentum characteristics, right? How each change seems to affect the quality of the regression relative to the multiple dimensions that we're attempting to optimize in this state case. So this system builds a high dimensionality space. Now, what happens here with regard to the dimensions? How many dimensions are there in this data set?
3.
Four. Because why? Why is there? Why indicates the height, elevation as a result of the changes on that surface, right? So this is technically a 4-dimensional graphic space. However, the space that is being described here decomposes somewhat, and you can combine these together in a variety of different ways to get different perspectives on what that surface might look like in 3D. However, the ultimate consideration is this is 3 error surfaces. So we could attempt to try to create a 3-dimensional version of the error surface of this, but that would be of the error surface, not of the original data set. So in order to graph the original data set, I need 4D. In order to create 3 data surfaces and combine them together, I still have a problem where I have 3 2-dimensional graphs, right? Still 4 dimensions, still problematic, because I need an additional axis for each graph that I bring in, right? So if I have the first 2 axes, then I have the second axis, where I put the other one. In between them, all right? So that's what we call a manifold or a hyperdimensional space, right? Something that goes beyond our capacity to adequately graphically represent or even sort of spatially understand. It is a 3-dimensional space moved through a surface, or moved through a volumetric revolution. So you end up with a surface of volume by translation through the space.
I have a question.
Yep.
So it's like if there is more than, suppose they are a 3-dimensional, we are understanding. So another dimension is there and we are passing through it, like that kind of?
So technically time is the 4th dimension, right? So
yes.
within the construct that we would look at, and we would say that I can see how beta 1 and beta 2 interact with one another, but the only way in which I can understand how that surface created interacts with beta 3 would be to have it move or relocate based upon the mean of beta 3. So I need to translate that whole section relative to the characteristics of that region. It's a sub-selection of the existing space. So the adjustment is high dimensionality beyond something that's easy to explain. But you can think about it in saying, what does a 3-dimensional object look like, right? What happens if I move a 3-dimensional object, right? The per Durantist idea is that you end up with, you have a cube and you move it through space, right? You have sometime t naught and sometime t1. There's a whole bunch of individual time steps in between that, in which the object, the 3D object, was in that location at that time. And so it essentially creates this little like quantum worm thing, right? Where it was in that position. So the 4th dimension is a movement of or translation of 3-dimensional objects through space, but the creation of a surface that is now in the manifold in 4D. So, if anybody ever seen the movie Donnie Darko?
Oh yeah.
Yeah, so the worm, where he's moving around and like he's leaving like an impression of himself in the past, that's a 4th dimensional representation of yourself, right? So I move from here, and then if like I overexpose the photo, I've got all the frames of me in between. I'm like a worm moving through space, right? All right, so let's think about one other one, and I want to just say this one as far as something that actually does create some interpretability. We have a target relative to American football players' season tackling average. That is In American football, we are violent and we jump on people, right? And knock them down on the ground. We do things that you can't do in other sports, but we're encouraged to do those things, right? So the idea here is that tackle average is related to proficiency of certain players, right? All players should strive to be good at tackling relative to this outcome, but there are specific players that are the best at it. And what would we think about would be best at somebody that sort of could jump on someone, grab them, and knock them down? Well, that's somebody that has relatively big person, right? They gotta be a big guy. So we say there's a factor of their weight. We also say that there's a factor related to their height. So I ran a regression relative to the weight and height of players that had the optimum tackling ratio, and what I discovered was that the output of likely target relative to that regression indicated some relative offset of the mean of the grouping plus 50% of the player's weight minus 10% of their height, right? So what's the minus indicate there? It indicates that the slope or the gradient there of the value is a negative slope. So it is the value descends as height increases. So as you get taller, you're not as good at tackling, right? Too high. You need a low center of gravity so you can grab the people, down low, right? I also have this consideration of the 50% for their weight. So the bigger you get, the more likely you are to be able to get those tackles, right? So if you weighed 600 pounds and you were 4'3", right, you should be the best tackler in the world. But that would be really pretty interesting. So anyway, the reason here is, what about this? What about the considerations? Height and weight. I did independent regressions there, right? They change with one another, right? Body mass index. The quality of the assessment is going to be based upon the idea that these two factors are technically linked to one another. So how do we interpret that characteristic of the negative value of height with respect to the idea that height and weight are correlated with one another? We have one value that increases and the other has a diminishing return within the same space. So you can't do an independent decomposition for the regression because of the fact that the two factors are related to one another. So you're going to need to create a surface that complements one another so that you can find the optimum, the settling point between all of those things, right? We recognize now from looking at it that this is an optimization. Don't be too tall, right? And don't be too heavy. All right, this one's nice, I like it. This guy is the guy that is credited for the box plot, right? So people think that that literally means the little boxes you put around it, but it's actually just named after the guy. It's weird. Whenever your name is box and you develop a plot that has a box in it, I mean, it's just like the destiny, right? The destiny to death. So it says essentially all models are wrong, but some are actually useful, okay? So I like to share this quote along with another quote that I like. It comes from a Native American book called Tonto and the Lone Ranger, Fist Fight in Heaven. Have you ever heard of it? It's a very interesting book. They made a movie about it called Smoke Signals. And there's a quote in there where there's a guy who he's a Native American storyteller. And he says, all stories are true. And some of them actually happen. Okay? So, that's the way in which we're looking at this here, is that all models are wrong to some degree, all right? They're never going to be perfect, but it is the utility of the model that makes it better for us. All right, there's only one way to find out what will happen in a complex system, and that's to poke it. You have to disturb it in order to understand how the system will respond to your perturbation, right? If we know that things are linked together, we must in fact have certain changes to the values and the corresponding ripples through that system in order to see how those correspondents interact with one another. I can't understand those correspondents by taking it piece at a time, and I must utilize the consensus of the information as spread across that higher dimensional space in order to extract that high complexity interactiveness out of that space. It will get good, it will get useful, but it'll never be perfect. So, I'm not doing anything special here, I haven't done anything new. What do I have?
It's just prediction.
Residual sum of square values is just gonna be the square consideration. All I've done is taken y hat and expanded y hat down in here into a full iterative operative, right? So I need to do this process of the difference between the target, the intercept, and each of the coefficients times each of the features for some specific instance, right? So where am I iterating across? I'm iterating across here, right? Sample 1, sample 2, sample 3, right? And I just plug these values into the representative elements within the array. The selection of the coefficients then becomes the minimization of RSS. So if I have some value for each output relative to that, I take the summation across the entirety of the data set. Now I'm doing this for multiple dimensions as well as multiple data points. So this idea becomes that the better my model is, we said previously we had H naught, that's just the beta hypothesis. We had H of A, that's where we have some coefficient characteristics and interactions. And then we have HB, which is our second version of the hypothesis. We look at the difference between HA and HB, and we determine, did cranking those knobs and changing those coefficients in that specific way cause an improvement between our original hypothesis, our original model between the interaction of the characteristics, and then the subsequent version, our next best guess. If we establish our next best guess based upon this idea of using a gradient assumption, you guys remember the idea of calculating gradient? Anybody ever done gradient calculations? Okay, cool. At least we have one person in here. So grad here, J, would be part of the Hessian of this decomposition, which would abstract to say that from any given surface point, I can calculate based upon the differential, right, between beta 1, some element beta, and some element of the output or the target of the system. So the accuracy then, right, so I say delta of error in that case. So however much the error changed as a result of the change in the coefficient, partial of decomposition of this taken times the gradient of this consideration ends up becoming the direction of the greatest increase in error. So as error increases, this is the surface of the increase in error. So what I actually want to do is I actually want to take the negative of the gradient. I want to go in the opposite direction. So since I know which way is the highest error increase, and which way, according to the surface generated by that calculation, that I have a positive net increase in error, meaning I'm going further away from the goal, I would assume that the absolute inverse of that system, right, the negative version of it would be in the direction of the highest increase in performance, right? So if the gradient says this is the worst direction, then let's take the opposite of that and we'll go that way. We should essentially effectively be going in the right direction. Now, if I can do that for each individual axis, then I can determine the ideal slope because the direction of the slope in the opposite direction should be the same as the inverse of the gradient, meaning that the intensity changing from was bad is now better, continue in that direction should have the same relative slope, and the steepness thereof tells me how much I can adjust beta each time. How big are the steps in between how I adjust that coefficient each time in order to try to create an improvement in that system? If you think about it here, we have T naught, T1. Let's just substitute this for some initial conditions for the beta 1 initial configuration, right? And then some subsequent additive value to beta 1. Right, so I had a value of beta 1 at like 0 or whatever. I add a little bit to beta 1, 0.001. I move and I get a little bit better performance. Right, now I've rejected the null hypothesis. Now I'm going to go to the second hypothesis. I'm going to say if I change that by the same amount, 0.002, then I should continue to move down the error surface, right? Start here, then move down, start here, and then I should keep going a little step at a time. Each one of these is a slight increase to the value of beta 1 with the hope of saying that as I increase the correlation or as I increase the assumption of the correlation between X and Y, that I would end up with a proportion that would be the correct proportion relative to the remainder of elements as well, right? So I get everybody's contribution, and I balance everybody's contribution such that I'm getting the right ratios of each person's relative value to the ultimate backup of the system. That is the RSS, the summational overall error as a result of these independent assumptions about the beta coefficients relative to that data set that contains a model, right? Within the data set is hidden. Our model is hidden in the data set, right? We're just teasing it out. We're just telling it to tell us its secrets, all right? So as we improve the performance of the model, right, we have a three-dimensional space. We're going to put a plane through the surface here, and the residual is going to be the summation of the distance of all of the points on the surface relative to the dimensions we're encountering. Now what happens here? Previously we just had the calculations for the points relative to a line. Now we're calculating in three dimensions, right, an x of 1, x of 2 to y. We have the summation there is giving us the distance to a surface. That's just a calculation from the current normal, right, the vector of translation to that point, and it is the vector product, the magnitude of the distance, or the difference in distance between x of 2's contribution and x of 1's contribution. So as I say, as I change initially with low values of x of 1 and x of 2, I have the lowest values of y, right? But I have a slightly lower increase in relative value along x of 2 than I do of x of 1, meaning that if I hold x of 2 relatively static, right, I don't increase it a lot, but I do increase x of 2, I should actually be increasing or getting hotter here, right? So the lighter the color is, the more towards green here, the higher the elevation. So this one says x of 1 increases along this axis, x of 2 increases along this axis, and the combination thereof is this surface of values, each space corresponding to the likely response or the balance in performance between the two states. Now, how can I tell that this is an improved performance over another model? I just have to utilize something like an adjusted R-square value to see whether or not it fits to this particular data distribution. Instead of doing it in 2D like we were with the systematic regression, now we do the true sum of, or total sum of squares and residual sum of squares as we were doing it in the previous slide here. I just do it for additional dimensions. So the ability to assess the fit here is going to come up with an array essentially that's going to tell me the quality of the fit relative to each of those dimensions and in the analysis. If I continue to improve the process, right, I'm going to end up with the output where I have intercept coefficients, relative coefficients for each of these operative items, right? We notice here the coefficient for newspaper is you're losing money, right? You know, you get a 0.1 times whatever value you point in, literally less. This is just pouring money down a rat hole. Okay, it doesn't do it literally almost doesn't do anything. But what it does do is take away from sales. Okay, so you're just like, I don't know how this works, but somebody sees this advertisement in the newspaper, and they're like, they advertise in the newspaper. Apparently, they have no idea what they're doing, right? So they're like. Why would you ever, that's wasting money. This company is dumb because they're wasting money on newspaper advertisements. I'm not going to buy something that they make because obviously it's probably designed as stupid as their advertising campaign, right? So I don't know if that's the reason why. I've always laughed at this because I look at it and go, how can seeing an ad in the newspaper make people less likely to buy the product, right? The only reason would be if they thought that, it indicated the company's lack of preparation.
There is another thing I want to say. It's like paper has like a static thing, but the television and radio have they are saying it and they are visualizing it, but the paper does not have the visual effect.
But you know what? This has changed over time too.
Yeah.
So we can look at this model for a current time step. Then we can actually create another version of the model for a previous time step. And we can compare the models both in their quality of fit to the data distribution as well as what changes the models occurred over time. right? What the preferences were. Let's look here, for instance, with regard to the correlations. This indicates the quality by which some value will change relative to a change in adjustment in a subsequent value, right? So how much an adjustment of TV causes with regard to radio's total value adjustment to what? So it's with this statement, this of course is just the upper triangular of this matrix, because the lower triangular is a mirror, and then the diagonal is an identity, right? So we're only concerned with those correlations. We only have 6 correlations between the 3 elements, but this tells us how they're related to one another, right? So newspaper and radio have a much stronger relationship to one another, and a stronger relationship to sales than newspaper, but TV has the highest sales correlation, right? So TV is doing the heavy lifting at approximately 78% of the relative power that your dollar has, or the number of advertisements that you're producing on that platform to generate a sales figure. This is how strongly that particular feature is linked to the target characteristics. So once we establish this correlation, where do we get this number from? The correlation coefficient, R, right? And the fit characteristic is just the square of that correlation coefficient. So this is the relationship of the square root of the fit of the model that tells us the output in this particular case, okay? So we've already actually talked about most of this stuff. We will cover F-statistic briefly, but we've mostly gotten through our linear regression material, so you should be able to do most of the things that are going to be required of you for Lab 3. I will post Lab 3 later on today, so you guys have a little bit over a week to work on that one. So that will be, the goal is probably have that one done like Saturday of next week, so we can start moving on to working in classification in chapter 4. All right? Yeah.
So you're telling us lab 3, but what's the lab 2?
Oh, so technically the first lab you did was lab for chapter 2. So lab 1 is chapter 2. So let's just let's say lab 1 didn't happen. So we just had lab 2. We started with lab 2, so count from 2. So 2 and 3. We're into chapter 3 now, so if you're looking at the, for your materials, chapter 3 lab is where we start off with the first of the regression. Thank you guys, have a good weekend.
Thank you.